Section 4.5, Complex Numbers. The properties of the complex number system. The complex number system contains all real numbers. Every real number can be written in the form of a plus 0I. So I'm going to make a little chart right here. So we have learned before that the chart, we have real numbers and then it broke down into rational and irrational numbers, and then rational numbers broke down to integers, whole numbers, and then natural numbers. Now, instead of just having the real number system, we also have imaginary numbers. And then every number in our whole world is a complex number, and the complex number form is written right here, which is a plus bi form. The real number system, the form is when you just have the a or the real part, where the bi or imaginary part is 0, and for imaginary numbers the form is bi, where the real part a is equal to 0. So some things that we'll see with imaginaries, we'll see the square root of negative root 3, and then we'll also see such things as I root 3 and so on. And we know that every number can be written in complex number form because for a real number, if we had the real number 3, we could write 3 plus 0I, or if we just had I root 3, we could write 0 plus I root 3. So that's the chart. Addition, subtraction, multiplication, and division of complex numbers obey the same rules of arithmetic numbers that hold true for the real number system. And there's one exception with the exponent laws, and if you want to read up on that, you can look at page 297 in your book. Always write square roots of negative numbers in terms of I before doing any simplification, and then we'll talk about some of this other stuff in just a little bit. So let's go ahead and take a look at imaginary numbers again. Remember that bi is an imaginary number where b is the real part of the number, but since there's an I, that makes it imaginary. And also remember that these are called complex numbers. If we wanted to solve an equation such as this, negative 4x plus 5i equals 8 minus 6yi, and I'm trying to solve for y. The way that I would do that is I would take the real part of the problem, which is here, and set them equal to each other. So negative 4x equals 8. And then I would take the imaginary part and set those equal to each other. So 5i is equal to negative 6yi. And then all you have to do is to solve in order to find out what x and what y would be equal to. So for this, if I divide by negative 4, I get x is equal to negative 2 here. And then on this other side, if I combine like terms, I would take this first, and I would probably divide the I on both sides, because if I divide by I on both sides, notice it's going to cancel out here and here because it's really equal to 1. So I get 5 equals negative 6y, divide by negative 6, and y is equal to 5 over negative 6 for your y. And now when you plug that in for x and for y, you would notice both sides would be equal to each other. The next thing we want to do is to perform the indicated operation and write as a result in the form of a plus bi, so complex number form. If I look at the first one for a, well, to do this, you just want to combine your like terms. What are my like terms? My real numbers. So 2 plus 1 gives me 3, and then my imaginary part is also like terms. So minus 3i plus I would give me minus 2i. And this would be my solution. So just like when we have variables, i's are also considered to be like terms, except for they have to be, of course, remembered to the same power. And then you just add or subtract the numbers in front. If I look at b, the difference here, I have to distribute that negative sign. So 2 minus 3i minus 1 minus I, and then I would combine my like terms. So the real part is the 2 and the negative 1, so that's just 1. And then I have negative 3i minus I, which is minus 4i. If I look at c, I'm going to distribute to each of my terms. So 4i times 2 gives me 8i, and 4i times 1/2 I would give me plus 2i squared. And we're going to learn the powers of I, but if you remember from Algebra 2, remember that, I'm going to do this off to the side, but I squared is equal to negative 1. So in this case, I would have to simplify this further because we're going to learn about the powers of I. So this would be 8i plus 2 times negative 1, which is equal to, and we're going to put this in complex number form, so 1 plus 8i, because it's always in the form of a plus bi. So your real part goes first and the imaginary part goes second. And I don't know why I just did 1. It should be, we're not adding them. I'm multiplying 2 times negative 1, so negative 2 minus 8i. For D, I would want to box or FOIL this out, whatever you prefer. So if you like to do the box method, fine. If you prefer to just FOIL, that's okay as well. And then when we do this, we would want to combine our like terms, which are right here. So I have 6, and then negative 8i plus 3i gives me minus 5i, and then minus 4i squared. Remember that I squared is really negative 1, so 6 minus 5i minus 4 times negative 1, and then that really means that becomes plus 4, so 6 plus 4 is 10 minus 5i, and of course remember to write it in your real and then your imaginary part, so complex number form. So why don't you guys do E and F on your own. So pause the video for a second, and then I'm going to write the answers up so that you can see it. So for this first one, when you do this out, you should end up with, notice these, if you remember for algebra 2, are complex conjugates. So when you multiply them out, you end up with 16 minus 20i plus 20i. So your middle terms cancel out, minus 25i squared. So these cancel out, and you're left with 16 minus 25 times negative 1, which ends up giving you 41. And then for F, remember this is 3 plus I times 3 plus I. And then when I FOIL or box this out, I end up with 8 plus 6I. The next thing we want to talk about are the powers of I. The powers of I start with I to the first power, which is just I. I squared, remember we said, is negative 1. I to the third power, we can simplify into I squared times I. Remember, I squared is negative 1, and I to the first power is just I. So negative 1 times I gives me negative I. And then I to the fourth power can be simplified into I squared times I squared. And remember, again, I squared is really negative 1. Negative 1 times 1 gives me 1. And if you look at these, as we learned in Algebra 2, I know that the powers of I are going to go in cycles of 4. So every time you have this, I to the first power is going to be equal to I to the second power, negative 1, I to the third power is going to be equal to negative I, and I to the fourth power is equal to 1. So we need to know these because when we're simplifying our equations, we want to simplify any powers of I that we can into one of these 4 things, I, negative 1, negative I, or positive 1. And we can do that by using long division or also by using remainders. Anytime I have a remainder with 1 left over, I know it's going to be equal to I to the first power, which is the same thing as 0.25 because you have 1 out of 4 for the cycle. Anything with a remainder of 0.50 would be like 2 out of 4, so 50. Anything with a remainder of 0.75 is going to be I to the third power, and anything with no remainder would be equal to 1, or I to the fourth. So again, to find higher powers of I, such as I to the n, divide n by 4 and match the remainder to one of the powers listed above. And just to show you that they go in cycles of 4, I also wrote up I to the 5th, 6th, 7th, 8th, and 9th power. So notice the cycle next would be I, negative 1, negative I, 1, and then I, and it would keep on going. But if I wanted to find I to the 73rd power, I wouldn't want to have to always count it out, so that's why we do our division. So if I divide 73 by 4, and then my remainder is going to tell me what I'm going to be working with. So I know that 4 goes into 7 once, and then 4 goes into 33 8 times. And so notice that I'm left with 1 left over. And so the reason I did those decimals is because notice that really we have 1 over 4, if you remember how we wrote our remainders before, so 0.25. So I know that I to the 73rd power is really equal to I to the first, which is just I, and that would be my solution. Had I gotten 2, then for a remainder, then it would be 2 out of 4, which is 0.25, which would be I to the second power, which would be -1, and so on. So if we look at I to the 54th power, I could do the same thing. I can take 54 and divide it by 4. You can do the long division way, or if you do this in your calculator, you get 13.50. And because of that, we know that if we have 0.50 for a remainder, that's 2 out of 4, which really means we have I to the 54th is equal to I squared, which is -1. And that's how you would use the powers of I to simplify any power of I that you have. The next thing we want to talk about is complex conjugates. The conjugate of a plus bi is a minus bi and vice versa. We call these conjugate pairs. Because a plus 0i and a minus 0i for each real number a, every real number is its own conjugate. But these conjugate pairs are important because if you look right here, if we were to multiply conjugate pairs out, if just in general a plus bi times a minus bi, notice we would get a squared for the first one, and then right here we get so that's our first term. So then a minus bi. So I guess it'd be easier just to write it out. So we have a squared and then minus a bi, and then we would get plus a bi, and then the last one would be minus bi squared. So when I do that, my middle terms cancel out, and I'm left with a squared minus bi squared, but remember I squared is really -1, so we get a squared plus b squared for my answer if you FOIL it out. Why do we use this? Because it helps us to simplify when we're using division, express the quotient -2 plus 5i divided by 1 minus 2i in standard form. If we want to put this in standard form, that means we have to get rid of our imaginary numbers in our denominator, because remember we said before we don't like to have radicals in our denominator, and remember I is really a radical, and so because of that I have to get rid of it or rationalize my denominator. And the only way that I can do that is by using my conjugate pair. So 1 minus 2i, the conjugate of that would be 1 plus 2i. And I would multiply my numerator and my denominator by this. So when I do my numerator, I get -2 times 1, which is -2. -2 times 2i would give me minus 4i. And then 5i times the 1 gives me plus 5i, and then 5i times 2i gives me plus 10i squared. And then I'm going to do my denominator. And now remember, your denominator, your i's should cancel out. If they don't, then you ended up doing something wrong. So this would be 1. And then this times this would give me plus 2i. And then this times this would be minus 2i. And then this times this would give me minus 4i squared. So notice we want to combine our like terms. These terms cancel out here. And let's finish our numerator. So we have -2. These are like terms, so that gives us plus 1i, which you don't need to write the 1, and then plus 10, and then I squared is really equal to negative 1, divided by, and in my denominator I have 1 minus 4, and I squared again is negative 1. So now we just need to simplify this. So when I do that, I get negative 2 plus, I should combine those together. So negative 2 minus 10 gives me negative 12 plus I over, and then I have 1 plus 4, which is 5. Now, if we want to write this in complex number form or standard form, we could leave it like this. However, technically, this is not the correct a plus bi form. Most of the time, you'll see people write it as 12 fifths plus 1 fifth I, and this would be the standard form with the a plus bi. However, I will accept both forms would be fine. So the next part we want to talk about square roots of negative numbers. If we are taking the square root of negative numbers, remember that the square root of a negative number, like such as negative b, is to be defined as I root b. Now, for this, remember when you're simplifying these, you always want to take out the I first. For example, if you have negative 5 times root negative 10 right here, you have to do I root 5 times I root 10, and then this would give you I squared, and then root 5 times root 10 is root 50. I squared is really negative 1, and root 50 simplifies into 5 times root 2, and then this would become negative 5 root 2, and that would be your solution. If you did not simplify this in terms of I first and you multiplied, you would have gotten negative 5 times negative 10 gives me root 50, and notice that this would not give you the same answer here, so this would be incorrect. So please make sure that you always simplify in terms of I first. So for A, we have negative root 5, so then this would become I root 5. If you look at B for this one, that's supposed to be a radical right there, but if we simplify this, we need to get rid of that negative underneath the radical, so this would be equal to 2 minus I root 11 over 5, and if we really put this in standard form, it would be 2 fifths minus root 11 over 5, and if you want to just leave the I in front, that's fine. Most times people will put it behind for standard form, but in front of there is okay. And then for C, why don't you guys see if you can multiply that out on your own. The next part we're going to talk about is finding all solutions to polynomial equations. Complex solutions can be found to equations that have no real solution. Every quadratic equation with real coefficients has solutions in the complex number system. That means whatever the degree is, that's going to tell you how many zeros you should have, whether they're real or imaginary. And then also remember that conjugate solutions are going to come in pairs. So if you have a plus bi as a solution to your polynomial equation, you should also have a minus bi as a solution. If we look at number 7, it says find all the solutions to 3x squared minus 5x plus 13. Now I can go ahead and, since it's quadratic, use my quadratic formula in order to find my solutions. So I know my a is equal to 3, b is equal to negative 5, c is equal to 13. Make sure it's in standard form before you do that, and then you get x equals negative b, so negative 5 is positive 5, plus or minus the square root of b squared minus 4 times a times c all over 2a. And when I simplify this, I get x is equal to 5 plus or minus root negative 131 over 6, which means our two solutions are imaginary. So we can write this in complex number form, which would be 5 plus or minus I root 131 over 6. That means if we were to graph this on our graph, you would not see the x-intercepts because they are imaginary. And if we write this in correct standard form, this would be 5 plus or minus, or 5, 6 plus or minus I root 131 over 6. And remember, that means we have both the plus and the minus for our answers. So these would be our solutions. If we went ahead and looked at the graph, I already put this in my graphing calculator, and notice when we look at this that our graph right here that we have does not cross the x-axis, which is why my solutions are imaginary. So then we want to do the same thing for number 8, find all the solutions of x cubed equals 64. Now if we take the cube root of both sides here, you would end up with x being equal to 4 if you solve. However, if you look at the degree is equal to, and I'm going to do this. So the degree is equal to 3, which means we should have 3 complex solutions. That means that if I have x equals 4, the other 2 could be irrational solutions or they could be imaginary. And since it says to find all of the solutions, we need to find those other ones. Now, the way that I'd want to do that is if I think about x cubed minus 64, I could set equal to 0. And if you remember how to factor, you could factor this. If you don't remember how to factor, you could always use synthetic division with the 0 that we found, which was x equals 4. So let's go ahead and do that, and then I'll show you guys how to factor. So if we put 4 here, it needs to be in standard form. So 1 and then 0 for 0x squared and 0x, and then negative 64. Because remember, this is factoring my equation in case I forget how to factor. So this is 1. 1 times 4 is 4. And this would be 16, and then 64, and then my remainder is 0. So this is x squared plus 4x plus 16. So I just factored my equation there. So remember, if we write this as x minus 4 times x squared plus 4x plus 16, it factors your equation. And if you remember, if you want to factor something that is cubed, if you have I'm going to write down the general formula. So a cubed minus b cubed would be equal to a minus b. So then you do your first term, a squared, and then take your two terms and you're going to multiply them. So minus is a plus here because it's minus plus plus. So plus ab and then plus b squared is the way that you do that. And if this was a plus here, this would be a plus minus plus. So you can do that for cubic equations, or if you forget how to do that, you could always use synthetic division and divide it and get your answer. So we're not done here because we want to find the other two solutions. And if I look at my graphing calculator by plugging x cubed minus 64 in and then hitting graph, and I had to, of course, since it's x cubed minus 64, I know that I'm going to hit a y-intercept of negative 64, so I changed my window so that I was at like negative 80 for the y values here. And if I look, I can see what my graph is looking like, and it only seems to cross over once, which means that the other two solutions are most likely going to be, or actually I can already tell you right now that they're going to be imaginary. So in order to finish this, we would have to use the quadratic formula on the rest of this equation. So when you do that, you get x is equal to negative b. So our a is 1, b is 4, and c is 16. So negative 4 plus or minus the square root of, and when you do all that, you get the square root of negative 48 all over 2. And then we can simplify this, so this becomes negative 4 plus or minus I root 48 over 2. The square root of 48 can still be simplified. So this becomes negative 4 plus or minus root 48 becomes 4I root 3, because you always put the number before the variables, over 2. And then we can simplify this by dividing each of these terms by 2. And remember, terms are separated by addition or subtraction sign. So this would be negative 2 plus or minus 2I root 3. So these are two of your solutions, and the other solution is x equals 4. So all of your solutions would be x equals 4 and negative 2 plus or minus 2I root 3. And remember that those solutions, imaginary solutions, come in pairs. If it then asks to write this in factored form, then our factored form, completely factored over the set of real numbers, would be this right here. But if we wanted to completely factor this equation over the set of complex numbers, it would be x minus 4 times x minus negative 2 plus 2I root 3, whoops, and negative 2 minus 2, or x minus, sorry, oops, x minus negative 2 minus 2I root 3, and then you could simplify that to make it look a little bit nicer. So this would be x minus 4 times x plus, because I'm going to distribute that negative sign, 2 minus 2I root 3, and x plus 2 plus 2I root 3. Now, like I said, remember, it didn't ask us to do that. The question just said to find all the solutions, which we did right here. But if it asked me to factor this over the set of complex numbers or to factor it completely, then this one that we just did would be my answer. Or if it said to factor over the set of real numbers, then this part right there that I just started in red would be my answer.